Okay, let's get started. Okay, hello everyone. This is SeungryongKim. Okay. Okay, so this is lecture 7. Lecture 3. But we have to finish lecture 2 first. Okay, so before that, let's recap what we've done so far. Okay, let's start with definition of the echelon form and earlier form, so reduced echelon form. So the echelon form of the matrix should satisfy these three kinds of the statement like this. So first statement, second statement, third statement. The general form of the echelon form should be looks like this, right? And if we low reduce this matrix further, we may achieve this kind of RDF form, reduced echelon form, looks like this. Yeah. Then why we have to consider the EF and REF form? Here's our strategy. So here is our original matrix, N by M matrix, by using the row operation, elementary operation, replacement, scaling, or interchange, right? We can make our matrix and in a echelon form, right? Then we can say that this matrix has solution or not, consistent or not, right? And then by further low reduce the EF form matrix to the REF form, then we can find the solution, right? Finally, then which is the solution of the original matrix, right? So this is our strategy. So this is going to be the topic of the today's lecture. Today's the low reduction algorithm. Anyway, so yeah, echelon form and earlier form. Earlier form is the unique, right? So here was the CR1 uniqueness of the reduced echelon form. Right. We also discussed the pivot position and pivot column, right? So when reducing the matrix A, we can find out the pivot position and pivot column, right? So blah 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 blah, like this. Finally, when we achieve the echelon form, we can finally find out pivot position and pivot column here, right? So in this case, right. In this case, these three position location is called the pivot position, and these three columns are called the pivot column. Okay, so today we will derive the low reduction algorithm. So this is very, very simple and straightforward. This is also called Gaussian elimination. Gaussian elimination. In Korean, 그 가우스 소거법이라고 혹시 들어본 친구들 있을지 모르겠는데 가우스 소거법이라고 불리죠, 그렇죠? So let's do that. But to derive this algorithm, we don't need the further notation or the further technique. We already discussed this one, but let's derive this algorithm in a systemic manner. So to derive this one, I'd like to show the one example, and I will summarize the algorithm. So first of all, the question was apply elementary operation to transform the following matrix first into the echelon form, and then into the reduced echelon form, or EF. Okay. So as we discussed so far, by using these two forms, echelon form and reduced echelon form, we can determine our matrix, our system has solution or existence, or and uniqueness, right? Uniqueness. Right. So let's do that. Here is our matrix A, and okay, there was the three laws, so maybe there exists three equations. and we have 6 columns. Okay, 3 rows and 6 columns, and so we can say that we have 5 variables. If we define this matrix A as a augmented matrix, right? So let's do that. So first thing we have to do is begin with leftmost non-zero column. Leftmost non-zero column. So we can just assume that this is a pivot column. This first column is pivot column, right? So in this case, the pivot position is at the top of this column, right? But in the original representation, the first element was 0, right? So to make this column, to make this location as a pivot position, we have to change row 1 and row 2 or row 1 and row 3, right? Because these two terms has a value, right? We can do that. So first of all, select non-zero entry in the pivot column as a pivot. In this case, if necessary, interchange rows to move this entry into the pivot position. So there are two possibilities, row 1 and row 2 or row 1 and row 3. But in this case, let's interchange row 1 and row 3. So this is the elementary row operation. So interchange R3 interchanged by R1. Look like this, right? This is a first strategy. But there are two kinds of possibility, R2 and R3. So how can I determine which columns, which rows is better? So to understand this, we have to discuss partial pivoting. In step 2 above, the computer program usually select the pivot, the entry in the column having the largest absolute value. This strategy called pivot position, partial pivoting, is used because it reduces the amount of errors in the calculation. Looks difficult, but it's very straightforward. I'd like to show you the one example. So let's also assume that we have a matrix 0, 1, 0.0, 3, 2, 3, 1, 1, 1, 1. Let's suppose that this is R1, R2, R3, for example. So to make this term as a non-zero, we can interchange R1 and R2 or R1 and R3. So there are two possibilities, right? So, okay. Case one means R1 interchanged by R2. In this case, our new matrix is going to be 1, 1, 1, 0, 2, 3, 0.003, 1, 1. Maybe we solve this this matrix, blah blah blah. Then our solution, the x1, maybe represented by 1 times x1, blah blah blah, right? Then our solution in this case it's going to be blah 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 over 1. What about second case? Maybe we can interchange R1 and R3. Then our new matrix is going to be 0.003, 1, 1, 1, 1, 1, and 0, 2, 3. Right. Maybe we can also find a solution in this case 0.003 x1, blah, 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 right? Then our new solution is going to be blah 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 over 0.03. Right. Ideally, this solution should be same. This solution should be same. But in computer programming, maybe you will study these kinds of concept in the computer structure, maybe computer structure. So when you represent your number in computer program, maybe this kind of computer program use the floating point or the some fixed bit, use fixed bit to represent your number. So for example, if your computer use 4-bit to represent your number, and for example, if your number 0.6666 blah 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 blah, then you have to round off. Computer use round off to represent your number, something like this. So there are some gap. So this gap is called round off error. Round off error. So, but when I use this one and this one, in this case, because the this 0.003 will maximize round off error because it can enlarge the values, so it can in this case the round off error will happens. I mean the getting worse in this case compared to the one, right? So in this case, it's going to be better to select this strategy to reduce round off error. So this strategy is called partial pivoting. Partial pivoting. So in other words, to reduce round off error in the calculation, computer program usually select the pivot entry in the column having largest absolute value. So in this case, 3 and 3 are equal, so you don't need to consider. But if the value, I mean this value is much higher than this one, for example 11, then we have to choose row 2 as a candidate. Okay, so this is called the partial pivoting. 네, 뭐 간단하게 한국말로서 설명해주면 뭐 어려운 얘기 아니고요. 그러니까 우리가 이제 이렇게 여기가 첫 번째 컬럼에 제로가 있는 경우에 논제로 밸류로 바꿔야 되는 경우가 많이 있죠, 그렇죠? 우리가 0이 나온 경우 많이 있으니까 그런 경우에 어쨌든 로우 2나 로우 3 중에 하나를 바꿔야 돼요, 그렇죠? 둘 다 이론적으로는 어떤 컬럼으로 바꿔도 값은 똑같아요, 솔루션은. 그렇죠? 왜냐면 리니어 시스템보다 로우 리덕션을 했을 때 솔루션이 같기 때문에. 근데 우리가 실제 컴퓨터 프로그램으로 이제 여러분들이 이 솔루션을 풀 때는 이렇게 어떤 4비트와 같은 어떤 비트 연산을 가지고 이제 여러분들의 밸류를 표현을 해요. 그러다 보면 이제 어쩔 수 없이 어떤 라운드 오프 에러들이 나올 수밖에 없어요. 그렇죠? 0.0066을 표현을 못하니 어떤 소수점 넷째 자리에서 뭐 반올림을 한다든지 그런 어떤 라운드 오프 에러가 이제 여러분들이 실제 프로그래밍 할 때 나오긴 할 텐데, 그런 경우에 뭐예요? 우리가 이렇게 이 바꿨던 이 밸류가 크면 클수록 유리하겠죠. 왜냐? 우리가 이 x1 값이 작아지기 때문에. 반대로 이 작은 밸류를 선택하면 0.003을 선택하면 이 값이 전체적으로 커질 테니 이 라운드 오프 에러가 커져 버리겠죠. 그렇죠? 그래서 이 파셜 피보팅이라고 하는 스트래터지는 여기서 이 절대값이 큰 값으로 선택을 하는 게 파셜 피보팅이다 라는 거고, 실제 사실 구현상에서의 문제이지 여러분들이 뭐 솔루션 손으로 이 문제들을 풀 때는 사실 크게 고려하지 않아도 돼요. 하지만 우리가 실제 손으로 풀 때도 이 라지스트한 밸류를 가지는 로우로 바꿀수록 유리하다 설명을 하는 거죠. Okay? Okay? So anyway, we'll receive this matrix. Okay. So the next strategy to make this original matrix to the echelon form, maybe we can eliminate this term as a zero. Term as zero. So this is R1 and R2 and R3. maybe our new strategy is going to be R2 is equal to R1, R2 minus R1. This is our new strategy, right? So let's do that. So original R 여기다 풀어볼까요? Original R2 was 3, -7, 8, -5, 8, 9, and minus R1 is going to be -3, 9, -12, 9, -6, -15. By adding these two terms, 0, 2, -4, 4, 2, -6, right? 6. Okay, so our new matrix is going to look like this. 맞죠? 2 마이너스 4, 4, 2 마이너스 6. 맞죠? 마이너스 6. Okay. So this was step 3. This was step 3. Use row replacement operation to create the zero in a whole position below the pivot. Whole position below the pivot. So this is pivot and this is the whole position below the pivot. So we create the zero here, right? We could have divided the top rows by pivot 3, but with 2 3s in C1, it's just as easy to add -1 times -1 times R1 to R2, so like this, right? Okay. In step 4, cover row containing a pivot position and cover whole rows, if any, above it, and apply step 1 through the 3 to the sum matrix then limit, and repeat the process until there are no more non-zero rows to modify. So our strategy is like that. Okay. Now we find the pivot position, right? So cover the row containing the pivot position, right? And find out new sum matrix. Let's say sum matrix, and apply step 1, 2, 3 again to further row reduce, and then finally we can achieve the echelon form of the original matrix. This is step 4, right? So in this case, with R1 covered here, right? The step 1 shows that C2 in the next pivot column here, right? Here. For step 2, select the pivot, the top entry in the column. So this is the first pivot, and this 2 is going to be a new pivot. Right? And let's apply step 2, 3 again here. This sum matrix. So let's suppose that this is R2 and this is R3. To further row reduce, we have to eliminate this term as a 0. So our new strategy is going to look like this: R3 minus 3 over 2 R2, 3 over 2 R2, right? So in this case, 3, -6, 6, 4, -5, and -3 over 2 R2 is going to be -3, and 뭐죠? plus 3 over 2 times 4 and -3 over 2 대충 쓸게요, 여러분. 여러분 계산해보면 되죠? 제가 over 2 times 4 -3 over 2 times -2니까 plus 2 and 3 over 2, 6, right? This term is going to be 6, -6, 3, and 9. So by adding these two terms, our final value, our final row is going to be looks like this. 해봐요. 이렇게 빼보면 이거 쭉 계산해보면은 없어지고 쭉 계산하면은 뭐예요? 1, 4 나오죠? 1, 4. Okay. For step 3, we could insert the optional step by dividing the top rows of the sub-matrix by pivot 2, but instead we add just -3 over 2 times to the top rows to the row below. 무슨 얘기냐? 이거를 3분의 2로, 2분의 3으로 할 수 있지만 먼저 얘를 이 로우를 2로 나눠서 얘를 1로 만든 다음에 그냥 3을 곱해서도 할 수 있죠. 똑같은 계산이죠. 그렇죠? 어쨌든 이렇게 만들 수 있다. Okay. So this produced the following matrix. Looks like this. So in this case, okay. So it was a pivot position and it was a pivot position. And when it covers the row containing the second pivot position for step 4, we are left with a new sub-matrix that has only one row. So this is the first row, this is second row. So this is our new sub-matrix, This new sub-matrix. So we can apply the step 1, 2, 3 again here. But in this case, step 1 through the step 3 require no work for this sub-matrix. And we have reached the echelon form of the full matrix like this. So we can say that this is the echelon form, right? Echelon form. So here we can determine original matrix has solution or not. Consistent or consistent or solution existence. Okay, so let's suppose that this is the augmented matrix. This is augmented matrix. Then, okay, so question is, this system has solution or not? System has solution or not? 자, 그러다 한번 질문하고 갑시다. 자, 이제 우리가 저번 시간에 배웠던 것부터 쭉 와가지고 이렇게 오리지널 매트릭스 이렇게 에슬론 폼까지 줄여왔어요. 그렇죠? 자, 뭐예요? 뭐 대충 얘가 x1, x2, x3, x4, x5, and this is the right-hand side values, right? Then this system has solution or not? 자, 한번 대답해 봅시다. 에슬론 폼까지 왔을 때 우리가 솔루션이 있는지 없는지 어떻게 알죠? 여기에서? 자, 여러분 한번 맞춰봅시다. 솔루션 있을까 없을까 이 경우에? 솔루션 갈리네요, 그렇죠? inconsistent. 한 학생 바꿨는데 다른 친구들 어떨 것 같아요? 솔루션이 있을까 없을까? 이 경우에 뭐 for example, from the row 3, x5 is equal to 4, right? Then we can find out another values. I mean x3, x2, x3, x1, x2, x3, x4, right? So to conclude, it has solution. This system has solution, and this system is consistent. At the end of this lecture, we will see why this system has solution from the echelon form, but we can guess it has solution, right? And let's move to the next page. Then, to find a solution, we can perform one more step to obtain the reduced echelon form. Then we can find a solution. Okay. So in this case, okay, this is echelon form, and we already know this one is pivot position. Then we may guess our echelon form, a reduced echelon form, should be looks like this. Blah blah 0 1 0 0 blah blah. Right. So this is maybe echelon form, reduced echelon form of this original matrix, right? So let's do further from here to here. by row operation, elementary row operation. So this is step 4. This is step 4. Beginning with the rightmost pivot, in this case here, so here, working upward and to the left, create the zeros above each pivot. If the pivot is not 1, make it 1 by scaling operation, because this is definition of the REF form. Whole pivot position should have 1, value 1, right? So let's do that. Okay, let's suppose that this is R1 and R2 and R3. So to make this term and this term as 0, we have to consider the two kinds of replacement operation. First of all, new R2 should be R2 minus 2R3 by to reduce this one as 0, right? And new R1 should be 어떻게 되죠? 아니죠. 맞나? 맞죠. New R1 should be negative 6 R3, right? Then we can make these two terms as 0, right? Please do it yourself. It's very straightforward, right? So by using this kind of operation, now we can make this kind of new matrix. So in this case, we used rightmost pivot in R3, 그쵸? 이거 써서 create zero above it and adding switch multiples of R3 to R2 and R1, 그쵸? negative 2 and negative 6, 그쵸? 이렇게 해가지고 이렇게 만들 수 있다, right? One more thing is that here, 그쵸? Here. So we want to reduce this one as 0, 그쵸? This one as 0. Then there are several kinds of ways to do this, but first of all, because we have to make pivot position as 1, so first of all, let's use scaling to make previous row 2 as it looks like this. And then create the 0 in C2, 그쵸? column 2 here by adding 9 times R2 to the R1. 9 times R2 to the R1. 그래서 어떻게 될 거냐? 이제 R1, R2, and R3라고 하면 new R1 is going to be R1 plus 9 times R2 하면은 얘가 제로가 되면서 쭉 이렇게 나오겠죠. 그렇죠? 계산해봐요. 어렵지 않으니까. 뭐 해볼까요? 9 plus 9 here and 내가 12, 그렇죠? 이 12에서 12 minus 18 here and negative 9 plus 18 here and 0 here and negative 9, 63 here. Then it should be looks like this. Okay, so we made this pivot position and this pivot position as 0, as 1, right? So finally, 3 remains. And scaling R1 dividing by pivot 3, then we can achieve this kind of matrix, right? So this is REF form. REF form. This is the reduced echelon form of the original matrix. Right? So here, from REF form, we can find out the solution of your matrix easily. Before discussing the solution, how to find a solution, let's summarize row reduction algorithm. This kind of process was called the row reduction algorithm. The combination of the step 1, 2, 3, 4 is called for the phase of the low reduction algorithm. Step 5, which produces the unique reduced echelon form, is called backward phase. In other words, okay, we have a matrix A. By using row operation, we can achieve EF form of A, which is called for the path or for the phase step 1 form. Then by further row reduce or by applying the row operation, we can achieve the REF form of matrix A, which is called backward phase step 3 in previous example, step 5 in previous example. Then this kind of process is called row reduction algorithm. So why we need this kind of row reduction algorithm? Why we need to derive this row reduction algorithm? To determine existence and uniqueness of solution. And if there is unique solution, we can find the solution from this REF form, which is going to be the solution of the original matrix A. So this is why we have to study the row reduction algorithm. 자, 오늘 이제 로우 리덕션 알고리즘까지 쭉 천천히 설명을 해왔는데 결국에 어려운 거 없죠? 결국에 우리가 지금까지 얘기했던 거랑 똑같은 얘기고, 결국 로우 리덕션 알고리즘은 뭐다? 우리가 오리지널 매트릭스 A에서부터 EF 폼으로 간 다음에 REF 폼까지 오는 저 어떤 이게 포워드 페이즈, 백워드 페이즈라고 불리는 거고, 스텝 1부터 4가 포워드 페이즈, 스텝 5가 백워드 페이즈다. 결국에 뭐냐? 우리가 REF 폼으로 오면서 EF 폼으로 왔을 때 솔루션 익지스턴스를 결정 내릴 수가 있게 되고, REF 폼으로 오면 솔루션을 정할 수 있고, 솔루션이 유니크한지 유니크하지 않은지까지 정할 수 있다. 결국에 우리가 어떤 시스템을 푸는 과정, 그러니까 결국에 시스템을 어떤 리니어 시스템을 로우 리덕션 알고리즘 풀 수가 있다라는 거죠. 그렇죠? Question so far. 자, 여기까지 질문 있나요? 여러분들 아마 여기까지 저번 시간까지 잘 따라왔으면 어려운 얘기는 없을 텐데, 복습 혹시 여러분들이 좀 헷갈리거나 이런 분들은 저희가 유튜브에 올려놨으니까 꼭 복습해야 돼요. 그렇죠? Question. No? Question? No? Okay, let's continue. So, this row reduction algorithm, the REF form byproduct, leads to explicit description of the solution set of the linear system when the algorithm is applied to the augmented matrix of the system. This is a very, very important important reason. When the algorithm is applied to the augmented matrix of the system, we can achieve explicit description of the solution set of the linear system from the REF form. That's why we use our row reduction algorithm. Suppose that the augmented matrix of the linear system has been changed into the equivalent reduced echelon form. Looks like this. Okay. So, for example, let's suppose that we have an arbitrary matrix A, and by applying the low reduction algorithm, we achieve REF form, then we can derive the solution from here. So let's do that. So in this case, if we achieve this kind of augmented matrix, then our associated system of the equation maybe x1 minus 5x3 is equal to 1, x2 plus x3 is equal to 4, 0 is equal to 0. 0 is equal to 0, right? So let's think about the solution of this kind of setting. So, okay, so we have to find out x1, x2, x3. Okay, the question is, what is solution of this linear system? 자, 이 경우 리니어 시스템 솔루션이 뭐죠? 자, 어떤 x1, x2, x3가 만족해요? 이 시스템을. So, which x1, x2, and x3 values okay, so make these three kinds of equation true statement. Which values? 무수히 많죠? Infinitely many. 그쵸? Non unique. 그쵸? For example, right? You're right. For example, if x3 is equal to 1, 그쵸? x3 is equal to 1, x1 is equal to 6, x2 is equal to 3. This is one possible solution, right? And x3 is equal to 2, then x1 maybe 11, and x2 is going to be 2. There are infinitely many solutions. So to derive this kind of infinitely many solution, maybe we can represent x1, x2, x3 as a 1 plus 5 x3, x2 is equal to 4 minus x3, x3 is equal to x3 itself, right? Like this. Okay. So here we will define the two more concepts. Variable x1 and x2 corresponding to the pivot columns. In this case here, so this first and second column was a pivot column. So variables corresponding to the pivot columns in the matrix is called basic variable. And other variable x3, which is not corresponding to the pivot column, is called free variable. So in this case, x1 and x2 was the basic variable, and x3 was the free variable. Okay. Then whenever a system is consistent, the solution set can be described explicitly by solving reduced system of the equation for the basic variable in terms of the free variable. Like this. Right. So x3 was the free variable, and x2 and x1 was the basic variable. So reduce system of the equation for the basic variable in terms of the free variable, right? This operation is possible because the reduced echelon form places each basic variable in one and only one equation. Each basic variable in one and only one equation, like this. So each equation only one x1 or only one x2, so it's possible. I mean, x1 and x2 basic variable can be represented by using x1, the x3 free variable. Right? Right. So again, we can solve the first and second equation for the x1, x2. Ignore the third equation if offers no restriction on the variable, no variable, right? So this one can be represented by this one. 그렇죠? x1 is equal to 1 plus 5x3, x2 is equal to 4 minus x3, x3 is free. Free means x3 can be any kind of value, any kind of the value, right? So state where x3 is free means that you are free to choose any values for the x3. Right? Anyway, this kind of representation is called parametric description of your solution. Solutions. Okay. That's why we induce REF form to represent your solution space in a parametric description. Right? So in other words, okay, if you have the original matrix A and by apply RRA, low reduction algorithm, to achieve the REF form, then you can say that okay, it has the solution. It has a solution, and the solution of this system is going to be x1 is equal to 1 plus 5x3, x2 is equal to 4 minus x3, then x3 is free. Right? So it's going to be the infinite solution. So this is the parametric description of your solution set. Okay? Okay, so question so far. One question was 형민 학생 질문 있었네. So that is the reason why we transform original matrix to the REF form. Right. That's why. Any other question? 아, 그래요? 아, 그래. 아, okay. Other question? 없죠? So, in other words, whenever a system is consistent, has free variable, then solution set has many parametric description. For example, for instance, maybe you can represent your original matrix like this. So how? By adding x3, I mean the row 3, I mean the last equation here. 그렇죠? Maybe in this example 어떻게 할 수 있나? By adding 5 times R2 to the R1, then you can achieve the new system like this. Then you could treat x2 as a parameter and solve x1 and x3 in terms of x2. Maybe looks like this. X1 is equal to 21 minus 5x2, x3 is equal to 4 minus 2, and x2 is free. Maybe you can do that. We would have the accurate description of the solution set by looks like this, but for the consistency between me and you, we will set free variable as a free value, and the basic variable we will represent the basic variable in terms of the free variable. So this is going to be our definition, but it's not necessary. But we will use this kind of notation from now on. 그렇죠? 근데 이제 뭐 당연히 얘기지만 이거를 억지로 우리가 R3, 그러니까 X3를 프리 배럴로 안 넣고 이렇게 X2를 프리로 놓고도 할 수 있어요, 뭐 억지로. 근데 사실 이 경우는 사실 뭐 가능은 하지만 실제로 우리가 파라메트릭 솔루션이라고 하면 우리는 프리 베어리블을 이 뭐 X3, 그러니까 피벗 컬럼이 아닌 애를 프리 베어리블로 놓고 피벗 컬럼은 이제 베이스 베어리블로 놓고 하는 게 일반적이다. 우리들 어떤 컨시스턴트한 어떤 뭐랄까요 솔루션을 말하기 위한 일반적인 방법이다라고 얘기하면 될 것 같아요. 알겠죠? 하지만 무조건 그래야 되는 건 아니다. 그렇죠? Okay, so we will see second theorem, existence and uniqueness theorem. Existence and Knight's theorem. Okay, so this theorem means like that. A linear system is consistent if and only if the rightmost columns of the unity matrix is not a pivot position. Not pivot position. That is, if and only if the echelon form of the unity matrix has no row of the column of the form 0, 0, 0, 0, 0, P with B is not equal to 0. B is not equal to 0. These two statements are same. These two statements are same. We already see okay, so I would like to show you this example. Here, okay. Okay, it was an earlier form. Okay, so theorem 2 say that if augmented matrix, echelon form of the augmented matrix has the column 0, 0, 0, 0, 0, and for example 4, it's going to be it does not have solution and it's going to be inconsistent. 그렇죠? But in this case, this last row it's not a form like this because it has the another values here. It has solution. But it was a previous example. 저번 주에 example이었는데 here this one, this was the last row, 그렇죠? In REF form or EF form, but the last row is called 0, 0, 0, 0, 0. It was not 0, 0, 0, 0, 0, P with P is not equal to 0. So in this case, we can say that this system has solution. This system has solution. Right? It's very, very easy and straightforward. Okay. So if and only if the echelon form of the unity matrix has no rows of the form 0, 0, 0, 0, 0, P with P is not equal to 0, then we can say that it has solution and the system was consistent. In other words, linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot position. Okay. For example, okay, we have a echelon form of the matrix blah 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 blah, but last row contain 0, 0, 0, blah blah 0 and 1, and maybe other terms are here, right? Okay, let's suppose that this is echelon form of the original matrix, but in this case 0 times xn is equal to 1. There is no solution that satisfies this statement. So we can say that this system does not have any solution. So this system is inconsistent, right? In other case, we can say that the system is consistent. Okay, and if a linear system is consistent, then the solution set contain either unique solution where there's no free variable, where there are no free variable, and infinitely many solution when there is at least one free variable, like previous example, right? So if a linear system is consistent, the solution set contain unique either unique solution or infinitely many solution. Okay, that's theorem 2. Existence and uniqueness theorem. I think we don't need to prove this theorem because it's very, very straightforward. As you can see this example, right? 그래서 너무 간단한 얘기죠. 우리가 EF 폼으로 바꿨을 때 마지막 로우가 00000 하고 마지막 밸류가 어떤 0이 아닌 밸류가 있으면 솔루션이 존재하지 않죠. 너무 당연하게. 그렇죠? 왜? 0 이퀄 뭐 1을 만족하는 밸류는 없으니까. 그렇죠? 그게 아닌 경우에 이게 0이 아닌 이 B 하나가 0이 아닌 경우에는 결국에 우리가 컨시스턴시 할 거고 컨시스턴트 할 거고 솔루션이 존재하는 경우는 두 가지 경우였죠. 유니크하거나 인피니트 메인 솔루션을 가지거나 right? 그렇죠? 유니크한 솔루션 그냥 표현하면 돼요. x1은 얼마, x2는 얼마, x3는 얼마다. 인피니트 메인 솔루션인 경우는 어떻게 하면 된다? 우리가 parametric description을 만들 수 있을 거다. metric descriptions of solution set으로 표현할 수 있을 거다. 라는 거죠. 그렇죠? To conclude, this is the last page of the chapter 1.2. So, we'd like to solve your linear system. I'd like to solve our linear system. So, this is our new strategy to solve your linear system using low reduction, the low reduction algorithm to solve your linear system. Okay. So first of all, okay, let's suppose that we can represent your linear system as a matrix A. First of all, write the augmented matrix of system A. 이렇게 표현하고 그 다음에 use low reduction algorithm to obtain equivalent augmented matrix in echelon form, and decide whether a system consistent or not. Whether system is consistent or not. How? By theorem 2. 그렇죠? theorem 2. 여기까지 보면 theorem 2로 알 수 있죠? 솔루션 있는지 없는지. 그렇죠? If there's no solution, stop. Otherwise, go next step. So this step is called the fourth phase of low reduction algorithm, and then continue low reduction to obtain the REF form. So it's going to be 뭐예요? Backward phase. And then because there is solution, in this case there is solution, that's why we low reduce further, right? Write the system of equation corresponding to the matrix obtained in step 3. Write the system of equation corresponding to the matrix obtained in REF form, and rewrite each non-zero equation from the step 4 so that each one basic variable is expressed in terms of any free variable appearing in the equation, which was called parametric description. Parametric description. Right. So in this case, if there is exactly one solution, we can just write the values. For example, x1 is equal to 2, x2 is equal to 3, something like this. But if there is infinitely many solutions, you have to represent your solution in a parametric description form. Okay, so this is your new strategy to solve your arbitrary linear system. Okay, that's it. 어렵지 않죠? 결국에 우리가 챕터 1, 2 오면서 하고 싶었던 요 장을 말하고 싶었던 거예요. 그래서 우리가 뭐 열심히 피벗이 뭐냐 이런 거 열심히 배운 이유가 결국에 요거 하고 싶은 거죠. 우리가 어떤 리니어 시스템이 있어요. arbitrary linear 시스템이 있고 그 arbitrary linear 시스템을 우리가 중학교 때 배웠던 것처럼 가감법으로 이퀘이션을 열심히 지어가면서 풀지 않을 거예요. 이제 우리는 어떤 매트릭스 폼을 나타내고 매트릭스에다가 로우 리덕션 알고리즘을 정해서 어그멘티드 매트릭스 폼으로 바꿔서 이 에실런 폼으로 바꿔서 솔루션이 있는지 없는지 먼저 체크를 할 거예요. 그 다음에 솔루션이 없으면 끝이죠. 솔루션이 없는데 그게 솔루션이 뭐 유니크한지 찾는 거 의미가 없잖아요. 그렇죠? 근데 솔루션이 있다 하면 이제 REF 폼으로 한 번 더 바꾸고 REF 폼으로부터 우리가 솔루션을 바로 찾아야 되든 즉 원 솔루션을 찾든 아니면 infinite many case인 경우에는 어떤 free variable로 가지고 parametric description 표현하자 라는 게 이제 우리의 시스템을 푸는 전체적인 과정이에요. 완벽합니다. 어렵지 않죠? Question. 질문이 좀 줄었는데 저번 시간에 비해서 어렵지 않죠? Question so far? No? 질문 있으면 주시고요. 자, 한번 의견을 좀 물어봅시다. 저번 주보다 이젠 질문이 많이 줄었는데 어려워서일까요? 아니면 여러분 너무 쉬워서일까요? 아니면 제가 설명을 너무 잘해서일까요, 여러분? 누구한테 물어봐야 될까? 형민 학생. 형민 학생. 아이고. 역시 답을 정해놓고 듣는. 아니 아니, 장난이었고 세번 장난이었고 정말 이해했죠? 여러분 결국에 어렵지 않은 내용들이었고 좀 데피니션들이나 시어럼 2개 정도 나왔었고 사실 이렇게 큰 증명이 필요 없는 얘기들이었어요. 이제 우리가 챕터 2로 넘어가면은 사실 좀 증명을 많이 해야 되는 시어럼들이 많이 나올 거예요. 근데 그때부터 조금 복잡해지는데 지금 시어럼들은 사실 증명이 필요 없고 너무 당연한, 어떻게 보면 너무 당연히 그래야만 하는 시어럼들이어서 여러분들이 그렇게 어렵지 않았을 거고, 혹시 이해가 안 된다는 친구들 please recap. Please recap. Okay? Okay. So the last question was the 민준, by 민준, matrix에서 0이 있는 로우도 반대 표기가 된다. Right, you have to do that because the size of the matrix represent your linear system. I mean the size of your linear system. You have to represent zero rows as well. Okay. Okay, so that's it. So let's move to the lecture 3, vector matrices and solution set. Vector matrices and solution set. So this is a lecture. This is chapter 1.3 and 1.4 and 1.5. Right? Okay. So before that, okay, chapter 1.3. Okay. So on Tuesday, Thursday, in this week, we will have a homework covering from chapter 1.1 to the chapter 1.4. So that's it. That's announcement. Okay. So let's move to the chapter 1.3, vector equation. Vector equation. Okay. So when I ask you in lecture 1, some of you are not familiar with the vector, the definition of the vector. So I would like to start with the definition of the vector. But it's very, very easy if you understand the matrix fully. So it's going to be very, very easy. So what is vector? What is vector? A matrix with only one column. Matrix only one column is called column vector, or just called vector, or just called vector. For example, 2, -1, or 1, 3, 6, blah, blah, blah. These kinds of representations called the vector. So n by 1 matrix, n by 1 matrix, n by 1 matrix. An example of the vector with the 2 entries is W is equal to W1, W2, where W1 and W2 are any real numbers, From now on, the set of the all vectors with the 2 entries is denoted by R2, where R means real numbers, exponent 2 is a 2 entry. So from now on, if I represent looks like this, we will read this one is R3 like this, blah blah blah. And R3 means our vector have 3 elements. 쉽죠? 뭐 설명할 필요 없죠 이거. 다음에 2 vectors in R2 are equal if and only if their corresponding entries are equal. For example, okay, let's suppose that from now on we will represent the matrix. I mean the vector looks like this. A 이렇게 표현할 거야 앞으로는. let's suppose that matrix A, vector A consisting of the 1 and -1, and vector B consists of the 1 and 1. Then we can say that vector A is not equal to vector B. Why? Because each corresponding entries are not equal. First element was equal, but second element was not equal, right? So we can say that vector A is not equal to vector B. But if the vector B consists of the 1 and -1, then we can say that vector A and vector B is equal. Okay. Arithmetic operation defined on scalar value can be almost, not almost. The elementary operation can be applied to the vector operation in most cases. For example, addition or scaling. For example, given two vectors u and v in R2 space, their sum is the vector u plus v obtained by adding corresponding entries of the u and v. For example, vector u is also like this, v is also like this, and u plus v is going to be the sum of the each element, 1 plus 2, -2 plus 5, then it's going to be 3, 3. So u plus v is equal to 3, 3. It's very easy. Scaling vectors, it's also very straightforward. Given a vector u and real number c, the scalar multiple of u by c, u by c is the vector cu obtained by multiplying each element in u by c. For example, the matrix vector u is equal to 1, -2, and c is equal to 5, and cu is equal to 5 times 1 and 5 times -2, right? Then it's going to be 5, -10, 5, -10, right? It's very easy. This is very simple example. Given two vectors, u is equal to 1, -2, v is equal to 2, -5 in R2 space, find 4u, -3u, -3v, 4u plus -3v. Let's do that. 4u is equal to 4 times 1, 4 times -2, so 4, -8. So -3v is equal to -3 times 2, -3 times -5. So it's going to be -6 and 15. So then by adding these two terms, by adding these two vectors, we can achieve the -2, 7. So 4u plus -3v is equal to -2, 7. 그렇죠? 어렵지 않죠? This is the vector equation. Vector arithmetic operation. There are several kinds of the representation for the vector in geometrically. This is called the geometric description of the R2 space or the vector space. Consider rectangular coordinate system in the plane, rectangular coordinate or the plane. For example, like this one, x1 and x2. 그렇죠? 이렇게 two axes consisting of the two axes. Because each point in the plane is determined by order of the pairs of the numbers, we can identify the geometric point a, b with the column vector a, b. For example, we can represent vector as a point in a rectangle coordinate system. For example, like this, and this, 2, 2, 3, 1, 3, -1, there 2, -1, like this. Or we can represent the vector as an arrow from 0, 0, vector, 0, 0, 2, 2, like this, or like this, or like this. So this kind of representation also represent vector in R2 space. Okay. We may regard R2 as a set of the all points in the plane. So in other words, R2 means whole possible vector, whole possible vector having two entries, for example, 1,1, 1,2, or 1,0,1, like this, blah, blah, blah. So R2 may be set of the whole possible in the plane. So set of the whole possible in the plane. Maybe R2. Right? R2. Right. Very easy. 너무 쉽죠? 그럼 빨리빨리 넘어갈게요. One more definition is parallelogram. Parallelogram rules for the addition, vector addition. Parallelogram means in Korean 평행사변형이에요. 평행사변형이라고 표현하는데 평행사변형. If vector u and vector v in R2 are represented as a point in the plane, so here's vector u and vector v, then u plus v corresponding to the first vertex of the parallelogram, whose other vertex are defined by u0 v. So this first vertex is going to be the u plus v. This is called the parallelogram rule. Why? We can easily prove this one. Okay, let's suppose that U consisting of the U1 and U2, and V consisting of the V1 and V2, and okay, so U plus V was the summation of the each element, U1 plus V1, U2 plus V2, blah, blah, blah. Okay, when we consider the first element, okay, first of all, X1 element, U1 plus V1. U1 is here and V1 is here. Then S1 element of the U plus V1 should be U1 plus V1. Similarly, second element, X2 element, should be V2 and U2, 그쵸? V2 and U2, and final U2 plus V2 should be, looks like this, U2 plus V2. So from here, we can just see U plus V should be the first vertex of the 네 번째 점이죠. First vertex of this parallelogram, this 평행사변형, 그렇죠? 이런 평행사변형의 어떤 꼭지를 표현할 수 있다. in geometric manner, 그렇죠? 어떤 geometric view에서 우리가 아까 UV를 합치는 걸 생각해 보면 이런 평행사변형으로 이렇게 표현한 어떤 스페이스, 그러니까 우리가 geometric representation에서 이렇게 벡터 아리스메틱 오퍼레이션을 우리가 이해할 수 있다라는 거예요. 어렵지 않죠? 제가 오늘 몇 시죠? 오케이. 오늘 여기까지만 합시다. question. First of all, 방지민 학생이 전산수학. Right. So our lecture is going to be online lectures, live Zoom online lectures by end of this semester. Unfortunately, 우리는 지금 사실 사람이 좀 많아요. 90명 가까이 돼서 좀 여러 가지 고민 끝에 이제 우리는 이번 학기는 비대면을 볼 거고, but our midterm exam and final exam will be done by offline exam. 그래서 우리 이제 오프라인 시험 볼 때 볼 거고요. 우리 강의는 계속 온라인으로 갈 거예요. 우리가 제가 공지 한번 다시 할게요. 이 부분은. 네. Any other question? Nope. Okay. So today we started with the vector, right? So from now on, we will formulate our linear system solving technique we will define the linear system solving technique in matrix and vector from now on. In other words, now we can represent your linear system as a AX is equal to B, X equals B, which is one of the most important equation in this semester. 오케이? 그래서 이제 여러분들 벡터까지 왔어요. 결국에 뭐 하고 싶은 거냐? 계속 우리 어떤 리니어 시스템을 AX equals B로 표현하고 싶은 거고, 그 X equals B를 표현한 다음에 어떻게 하면 더 잘 풀 수 있을까? 어떻게 하면 efficient하면서 effective하게 풀 수 있을까에 관한 거를 이제 우리가 이번 학기에 이제 배우려고 하는 거고요. 그걸 위해서 이제 우리가 이번 lecture 3부터 이제 벡터 이퀘이션으로 들어왔습니다. 알겠죠? 이제 우리가 다시 한번 열심히 한번 달려보고요. 혹시 아직 이해가 부족한 친구들 오늘 강의 우리가 그 유튜브에 올려줄 테니까 꼭 복습하시고 우리는 목요일날 보도록 하겠습니다. Final, last question. 없죠? Okay, this is end of today's lecture. Thank you very much and see you Thursday. 여러분들 고생 많으셨고 우리 목요일날 뵙겠습니다.